Hello everyone, I'm Balamurgan. I'm from Vella Institute of Technology, VIT. I'll be uploading this video as a part of my digital assignment for the subject Computer Architecture and Organization. I'll be talking about IAS Architecture. So, coming to the introduction, what is computer architecture? Computer architecture is defined by computer structure and behavior as seen by the programmer. Computer architecture is nothing but the computer structure which we have for any machine. This includes the instruction formats, addressing modes, instruction sets, and general organization of the CPU registers. Here we go. What happens is, in the previous system, in the previous all kinds of systems, they were very primitive. We had to input all kinds of data into the system, which makes work very tedious. So we had to come up with a better system or a better architecture for the computer. This was known as von Neumann architecture or the IAS computer architecture. The new concept involved in this is the stored program concept. So basically, the computer architecture was divided into three parts: processor, memory, and the input output. So processor is further divided into two parts: control unit and the ALU. The control unit, it executes the program, and that data is being sent to the main memory. So the main memory stores the data as well as the executed part of the program. The ALU, it does the arithmetic and the logical operations, and it sends the final result to the output box. Coming next to instruction format. An instruction will be set in terms of words. So 1000 locations means 1000 words. So excuse me. These 1000 words has a total capacity of 40 bits. So the memory format can either be given in terms of data or instructions. If I'm giving it as data, the first bit, that is the 0th bit, will be taken as a sign bit, and the next 39 bits will be given for the number, that is the value or the number size. Second, if I'm giving the memory format as an instruction, it has a total of 40 bits as I've told before, and it has been divided into two parts: left instruction and right instruction, each of 20 bits. The left instruction has 8 bits for the opcode and 12 bits for the address. I repeat, 8 bits as the opcode and 12 bits for the address. This bifurcation is similarly there in the right instruction as well. So next, we're going to come to expanded structure of IAS, or the more abstract and the detailed structure of IAS architecture. So all these boxes, each of them, they show a register. So memory buffer register, the most important one, it has a direct contact with the main memory. So all data which has to either come inside the architecture or go out of the system should be to the memory buffer register. It acts as a central point. It is connected to the main memory, the input output, the ALU, and also to all the other registers. So it acts as a central point. Memory address register. It specifies the address in the memory of the word to be written from or read into the MBR. That is, the memory address register, it gets the address which from the program counter or sorry which gets the address from the program counter or from the MBR. Information register. The 8-bit opcode. The 8-bit opcode will be stored in the information register. IBR, it contains the right hand side part of the instruction. It contains this right hand side part, 20-bit right hand side part of the instruction. I'll be explaining this in detail in the upcoming video. Upcoming part of the video, sorry. Next is program counter. As you all know, the program counter, it contains the address of the next instruction pair to be fetched from the main memory. The accumulator and the multiplier quotient. The accumulator multiplier quotient, it gets the output from the ALU, that is after doing all the logical operations. The final result is stored in the accumulator and the multiplier quotient, which is further sent to the output box. So the instruction, IAS instructions, it has a total of 21 instructions divided into 5 parts: data transfer instruction, unconditional branch instruction, conditional branch, arithmetic, and address modifier. The data transfer. Each instruction, that is each symbolic representation, each instruction has a unique opcode. So see, an opcode consists of 8 bits: 1, 2, 3, 4, 5, 6, 7, 8. So every instruction has its unique opcode or a binary code for the computer to understand. First, data transfer. If I give load MQ, the computer has to understand the word load. So I give the input in terms of a binary code, which is also known as an opcode in this case. So load MQ means it transfers the contents or the value present in the MQ register to the accumulator. When I give load MQ, MX, it transfers the value of M of X, that is the value of the memory address of X present in the X register, to the MQ register. Store MX is the vice versa. It transfers the contents from the accumulator to the MX register. And next one is load MX. Transfers MX to the accumulator. Load minus MX. I transfer minus MX. Mod MX means the absolute value, and minus mod MX some value. Next, unconditional branch. Even this has its own instruction and a very unique opcode. So jump M 0, 0 to 19. 0 to 19, as I've told, the address, that is it takes the left part of the instruction. The next instruction will be taken from the left half. I've told these first 20 bits, that is the left instruction, will be taken when I give jump 0 to 19, and when I give jump 20 to 39, it will take the next 20 bits, that is the right hand side part of the instruction. Conditional branch. Conditional branch, as the name suggests, it has to be given a particular condition. So when I give jump plus M0 to 19, so the condition is if the number in the accumulator is a non-negative value, it takes the instruction from the left half. If the number is a non-negative value, when I give 20 to 39, it takes from the right half. Arithmetic. Arithmetic is just the basic operations: addition, subtraction, multiplication, and division. Addition, the value is added and the final value will be stored in the accumulator, and similarly subtraction, multiplication, division, where each of the operations takes place and the final answer, the final solution, will be stored in the AC, that is the accumulator. LSH and RSH. You can see there's no right part over here. This is pretty interesting because this also comes under arithmetic. Left shift. Left shift means shifting every bit to one side to the left. This is equivalent to multiplying the accumulator value by 2. So this comes under arithmetic instruction set. And RSH means dividing the value in the accumulator by 2. So this again comes under arithmetic instruction set. Address modify. Address modify means I need to store the left part of the address when I give 8 to 19 and the right part of the address. I've already told before, the address consists of 12 bits. So when I give 8 to 19, it stores the left address of the instruction, and when I give 28 to 39, it stores the right part of the instruction, the first 12 bits. So if I have to solve a question, this is a question where I'm given load mx500, add mx500 with that's the first instruction, and the second is store mx500 and other instructions. So the program counter value is 1. This 1 will be again transferred to the memory address register. As I've told, the memory address register gets value either from MBR or from PC. As I need to start with the first instruction, the program counter value will be 1. This is transferred to MAR. So the MAR takes the instruction of the first thing, that like MAR equal to 1, and it goes to the main memory. From the main memory, I can see that the information is load MX500 and MX500. So any kind of data, it first goes from main memory to the MBR. So the value of MBR will be again be uploaded in the left hand side box, as you can see below. So the MBR consists of two parts: load MX500 and add MX501. This information is again bifurcated into two parts: left part and the right part. The right part of the instruction comes to IBR. Yeah. So as you can see, one second. So the solution which was given in the MBR was divided into two parts. The load part of the MX, it comes to the left hand side, and the address part comes to the right hand side. So the MAR is equal to 500. This value goes back to the main memory, and this main memory will again go back to the memory where it's given that the memory address value 500 contains a value 3. So this 3 will again be further transferred to the MBR. As now we can see, the MBR value is 3. And this value of MBR is further transferred to the accumulator, and so the accumulator value is also updated as 3. The other part of the instruction, that's add mx501, the right hand side part of the instruction goes to the IBR followed by IR. The IR contains the opcode and the MAR contains the address part, which is 501. Okay, I repeat, so the first instruction was divided into two parts. So now talking about the second part, add mx 501. This add mx 501 goes to the IBR because it's the right part of the instruction. From there, the first 8 bits IR contains the opcode, that is add mx, and MAR contains the address specified in the instruction, which is 501. So MAR, as we know, the program counter value becomes 2 because I'm going to the next instruction. MAR value 501 goes to the main memory, and the next value from the MAR 501, which is given in the main memory that the value is 4, gets updated to the MBR. And add mx MBR, it goes back to the accumulator where the addition takes place, and the value of the accumulator gets updated to 7 because the initial value in the accumulator was 3 and the next value goes as 4. As I'm giving my instruction in the IR as add, it becomes 4 plus 3, 7. This process takes place again and again because the next program counter value becomes 2, the value of 2 comes back to the MAR, and the MAR again processes the instruction which is given in the main memory, which is store mx500. This process keeps happening term by term. Instruction format. An instruction format is divided into two fields, the opcode field and the operand field. This operand field is further divided into 1 or to 4 fields or even more than that. So the opcode always consists of 8 bits, whereas the operand is nothing but the address. I can give it in terms of 4 address, 3 address, 2 address, or even 1 address and 0 address. So I'll be explaining only 3, 2, 1 and 0 address instructions. How to violate the arithmetic statements in 0, 1, 2, 3 address. Symbols: addition, subtraction, multiplication, divisions. As the name suggests, it's for arithmetic operations, move for transfer type operation, load and store for transfers to and from memory and AC registers. So let me take this simple example. X is equal to a plus b star c plus d. If I'm going to use 3 address instruction, which is basically I can use 3 registers, each address field specified to a particular process register. So 3 address instruction means I can use 3 registers. First, I need to perform the addition a plus b. So I give add r1, a, b, which means the value of a and b are added and it is stored in r1. Similarly, I give r2, c, d, which means the value of c and d are added and this value is stored in r2. And next, I need to perform the asterisk multiplication operation. So I go multiply x, r1, r2, where m of x, that is in the place of x, r1 star r2 is stored. So I get the final solution as a plus b star c plus d. This is the method of simplification using 3 address instruction. Next is 2 address instruction, where I should use only 2 registers. I'm taking the same example. Move r1, a, which means the value of a is moved to r1. I need to add the value of b to the value which is present in r1. As we know, the value present is r1 is a, so I do a plus b. So I get this part. Next, similarly, I move the value of c to r2 and add r2, d, which means d and c are added. Now, I'll add the value of a plus b in r1 and c plus d in r2. I need to find the multiplication between these two. So this becomes a multiplication r1, r2. So this r1, r2 will be stored in the accumulator. I need to move this value, the multiplication r1, r2, r1 star r2 will be stored in r1. I need to move this to a value called x. So this value present in r1 register will be moved to x. So x contains now this valuable expression. So a similar example using a one address instruction. One address instruction means I just need to use a one register. I load A and I need to add B to it, and I store this value of A plus B in T. I load C and I add D to it, and I store this value in other variable. For example, I can just say I store it in R. I need to multiply T. If I give multiply T, it means this value of T is multiplied with that of R, and I store this T star R in X. So my final value of X will contain this expression. I repeat, I load A and then I add B. This A plus B, I store it in T. I load C and I add D. For suppose I load C and add D. This add D will contain the value, this D will contain the value of C plus D. So I multiply this with T, which means this T is multiplied with the value that is already present in the system. So I get a plus b star c plus d, and I store this value present in the system in another new register called x. Zero address. This is basically used for stack operations. So I need zero address is when I just need to use a stack to perform this set of operation, because there is no use of a register. I just need an empty stack, an empty file, sorry, stack. So push A, push B, and I add them. Push C, push D, and I add them. And when I give multiply, I get the value. And when I give pop, it has been popped out of the stack, and I get the final result. I repeat, push A, the value of A is pushed into the stack. B, the value of B, push B, it's again inserted in the stack. And in the stack, I have the value A and B. So I add them. I get A plus B. Now I push C, I push D, and I add, which gives me the value C plus D. When I multiply, I get the result of 1 multiplied with the result of 2. When I give pop x, this value present in the stack has been popped out, and it has been inserted to another value called x. This is another example. You can pause it and you can go through this example. It's also pretty simple. Addressing modes. Addressing mode is nothing but the way the operands are specified in the instruction. It's just that the operands given in an instruction, each can have its own meaning. So the operation to be performed is indicated by the opcode, and every addressing mode, there are various kinds of addressing modes: implied addressing mode, immediate addressing mode, direct and indirect, register direct, and register indirect. Also followed by displacement addressing mode, relative addressing mode, indexed addressing mode, and the last, auto increment and auto decrement. Immediate addressing mode. Immediate addressing mode is nothing but it takes the direct value given in the effective address uh, register. So it used direct program initialization. So the direct initialized value will be go to the immediate addressing mode. Direct addressing mode. The value which is being given in the instruction, that is the address part, will directly point, will give a direct pointing to the operand which is present in the memory. This is known as direct addressing mode. In the case of indirect addressing mode, the address value present in the instruction will point to a particular value in the memory. This value which is present in the memory will act as the address and point to another operand. This is my effective operand, and this will act as my address. You can just go through all the text. Register addressing diagram. So in the case of register, the register value will be given. This register value acts as an address. I repeat that suppose the register value given is 400. This register acts as a 400, and I need to search in the memory or in the register memory for the value 400. So the 400 is my effective address, and the data which is present in 400 is my operand or my final value. Register indirect. It's similar to indirect addressing mode, where the register address acts as the address. It points to an operand. This further points to another operand in the main memory. This is register indirect. Auto increment and auto decrement. Auto increment, as the name suggests, I increment the value, and auto decrement means I decrement the value by 1. Auto decrement, it takes place in the next or the succeeding operation, whereas auto decrement, the decrement first takes place and then it takes place in the addressing mode. Relative addressing mode is the direct address part of the instruction plus the value of the program counter. We know what the program counter is. Value of the program counter will be the next address to be specified. Indexed addressing mode. The index addressing mode will be the value of the index register added to the initial address, that is the initialized starting address. Now, we can solve an example. Given that the value of program counter is 200 and my initial address is 500, R1 is 400, XR is my index register with the value 100 and AC. As I've told, we'll start from the basic. Immediate operand. My effective immediate operand, as I've told, is the address which contains the effective address, which is 201. So the value 201 will be my immediate address. Immediate operand will be 201. Talking about direct address. Direct address is the initialized address which is given over here, which is 500. Next is register direct. The register direct is that the value register direct does not have any particular value. The register direct, the value 400, it does not point to any particular address. Register direct means the value 400 will be my effective operand. Now coming to register indirect, this 400 will act as an address That is, this 400 will act as an address and point to a particular one in the main memory, which is 400. This 400 points to 700. So the value 700 will be my effective operand and my effective address will be 400. We have completed immediate operand, register direct, and register indirect. Next, coming to direct address. Direct address is already told 500. Indirect address. So this value 500, 500, my effective address, it it has the value 800. This 800 further points to the value 300. So this 300 will be my effective operand, and this 800 over here, which will be my effective address. I repeat, what happens in indirect mode is that my effective address 500, it will point to a particular value in the main memory, which is 800. This 800 will be the pointer to the operand. So my effective address value will be 800 and my effective operand value will be 300. Remaining, we have relative address, indexed address. Relative address is the value of the program counter to the initial address value 500. So we know what the program counter means. Program counter is the address of the next instruction. So the address of the next instruction is 202. So my relative addressing mode will be 500 plus 202, which is 702. So my effective address will be 702 and my effective operand will be 325. Sorry, talking next will be index addressing mode. Index addressing mode is the sum of the index register and the initial address value. The initial address value is 500, which is be added to my index register, which is always already given in the question as 100. So it'll be 100 plus 500, 600, which will be my effective address. To find the effective operand, I need to find what is the value, that is what the 600 value points to in the main memory. The 600 points to 900, so my effective operand value will be 900. Effective operand value is nothing but the content of the accumulator, and 600 will be my effective address. Auto increment. Auto increment will be 400. I told before that increment takes place from the next operation, and auto decrement, the decrement first takes place, that is 400 becomes 399, and then decrement takes place. So 400 points to 700. The value of 400, it points to 700, and the value 399, it points to 450. So in this lecture, we've learned about the von Neumann architecture, the need for a von Neumann architecture, the basic memory formats, the expanded and the architecture of IAS, and how exactly an instruction is actually classified, the number of bits for opcode, number of bits for the address, and the working of a von Neumann machine, the total working and the explanation has been given. Next, we talk about the instruction formats, how a simple given expression can be expressed in terms of 3-bit, 2-bit, 1-bit, and 0-bit. And last, we talk about addressing modes. So you can go through these topics once again, and you can ping me up if you have any doubts. Hope this video was helpful. Thank you.